cut half of your liver out right now. Take a knife, remove exactly 60% of the tissue, discard it. What remains isn't enough to do anything, right? Wrong. What remains is enough to keep you alive, and over the next few weeks it will grow, reorganize, and occupy almost all the space the rest left behind. Not approximately, not crudely, functionally, precisely, vascularized, as if the part that disappeared had never existed. No other solid organ in the human body does this. The heart doesn't, the kidney doesn't, the pancreas, the spleen, the lung, none of them. If you lose enough tissue from any of these organs, the loss is permanent. The body builds scar where there used to be function, but the liver follows a different rule, a biology so unusual that physicians still debate exactly how it works, and molecular biologists still haven't reached consensus on the signal that triggers it all. What we do know is the result: 75% regeneration in 3 weeks. In some cases, less time. Before getting into how that happens, you need to understand what a liver is, because most people have a vaguely correct and completely insufficient idea. The liver is not just the organ that filters alcohol. That's like saying an airplane is the thing that carries your luggage. Technically true, catastrophically incomplete. The liver weighs between 1.2 and 1.5 kilograms in a healthy adult. It sits in the upper right quadrant of your abdomen, partially hidden by the rib cage, and has a reddish-brown color that looks almost artificial, like industrial plastic dyed with blood. Inside, its structure is hexagonal. Not metaphorically, literally. The functional units of the liver, called hepatic globules, are organized as microscopic hexagonal prisms, stacked and interlocked like a three-dimensional honeycomb of flesh. At the center of each hexagon is a central vein. At the vertices are portal triads, a set of 3 structures, a branch of the hepatic artery, a branch of the portal vein, and a bile duct. Blood enters at the vertices, passes along rows of hepatocytes arranged radially like wheel spokes, and exits through the central vein. Each lobule is a factory. And what does this factory produce? The list is absurd. The liver synthesizes most of the proteins in the blood, including albumin, the protein that maintains osmotic pressure and prevents your tissues from swelling with fluid. It produces clotting factors, without which a simple cut never stops bleeding. It metabolizes amino acids, converting nitrogen into urea that the kidneys later eliminate. It breaks down old hemoglobin, processes heme into bilirubin, conjugates that bilirubin, and sends it to bile. Its blood needs energy. It metabolizes drugs, alcohol, hormones, environmental toxins. It produces bile about 1 liter a day, which goes to the small intestine and emulsifies fat. So, pancreatic enzymes can act, and this entire organ, when cut in half, grows back. What triggers this process is something science took decades to begin answering. The most accepted theory today involves a concept called functional liver mass, the idea that the liver constantly monitors the relationship between organ, size, and the body's metabolic demands. When part of the liver is removed, that relationship falls out of balance. The remaining tissue senses it is overloaded, not metaphorically, chemically. The concentration of certain substances in portal blood changes. Pressure within hepatic vasculature changes, and this change triggers a cascade. The first signal biology identifies is an increase in growth factor concentrations in portal blood, the extreme coming directly from the intestine bathing the liver with everything absorbed from digestion. Among these factors, the most studied is HGF hepatocyte growth factor. HGF binds receptors on hepatocyte surfaces, the main liver cells responsible for 80% of organ volume, and activates intracellular, signaling that essentially says one thing: divide. Hepatocytes are cells that, under normal conditions, almost never divide. They're highly specialized, packed with metabolic machinery, and spend most of life in a state called quiescence, a cellular standby mode where they work without proliferating. When enough HGF appears, that mode shuts off. The cells enter the cell cycle. They replicate DNA, and then they divide. But it's not just TNF-alpha, IL-6, EGFT, GF-alpha. There's an orchestra of signals that must appear in sequence, at the right moments. Remove any component of this cascade in lab mice, and regeneration fails or is compromised. The system is partly redundant but has critical nodes, and the part not fully mapped yet is the stop signal, what tells the liver it has reached the right size and can stop growing, because it stops. That's what separates liver regeneration from tumor growth. A tumor is also uncontrolled cell growth. The difference is that a regenerating liver knows when to stop. It doesn't grow indefinitely. It grows until reaching a mass matching the body's metabolic needs, not necessarily the same size as before, but the size required for function. In rats, classic experiments show that if you remove 70% of the liver and transplant the removed tissue elsewhere in the body, the remaining liver grows back to original volume, but the transplanted tissue doesn't grow beyond minimal functional size. The body knows it already has enough liver. Communication happens through the blood. We don't know exactly which molecule delivers the stop signal. TGF-beta is the most studied candidate. It has anti-proliferative effects on hepatocytes and rises late in regeneration. But experimentally blocking it doesn't prevent stopping, so other mechanisms operate in parallel. This gap isn't small. It's one of the major open questions in hepatic biology. Imagine waking after surgery. You're in an ICU bed. Drains come from your abdomen. Monitors show vital signs, and somewhere inside you, where there was once a full liver, now there's just over half. The surgeon removed 60%. Technically, the operation succeeded. Technically, what remains keeps you alive for now. Over the next 72 hours, you feel the weight of that for now. The remaining liver performs full work with 40% capacity. Bilirubin accumulates, mild jaundice may develop. Albumin levels fall as protein synthesis lags behind demand. Mild coagulopathy may appear as clotting factors drop. Glucose must be monitored closely because glycogen release capacity shrank with organ volume. That's what medical staff see in tests. What you feel is different. Fatigue that ISNT, sleepiness, a metabolic exhaustion, like the body running in power-saving mode, nausea that comes and goes, diffuse malaise, hard to localize. Appetite disappears, biologically ironic because the liver needs nutrients to grow, amino acids, glucose, lipids, and you don't want to eat. 2 days after surgery, something begins. Remaining hepatocytes receive the signal. Growth factors and portal blood are elevated. Cells entered the cycle. Most adult hepatocytes haven't divided in years, maybe decades. Now they synchronize in a wave sweeping the liver like a growth front. Paraportal hepatocytes divide first, then more central ones. A dividing hepatocyte doesn't stop working. Unlike many cells, pausing function during division, hepatocytes keep metabolizing, synthesizing proteins, producing bile even while duplicating DNA. They don't have the luxury of stopping. The body can't wait. Week 1. Liver volume measurably increases, visible in imaging. Cells divided once, twice, lobules thicken. Vasculature adapts. Sinusoidal endothelial cells proliferate too. The liver isn't just growing, it's reorganizing. Week 2. Symptoms improve. Bilirubin normalizes, clotting time stabilizes. Appetite returns, both a sign of metabolic recovery and fuel for continued growth. Feedback becomes elegant. Better function improves appetite. More intake supplies, substrate, growth accelerates. And what makes this even more impressive is that regeneration isn't just cell growth, it's structural reorganization. Hexagonal lobules must be reconstituted. Vasculature must branch again. Bile ducts must reform. The three-dimensional architecture, allowing liver function, alignment of hepatocytes along sinusoids, cell polarity, cell-to-cell contacts, determining secretion direction, all must be rebuilt, and are rebuilt. In 3 weeks, in an adult human, the most natural question here is, why the liver? Why does this organ have a capacity no other solid organ has comparably? The answer likely relates to its evolutionary role as the organ most exposed to toxins. The intestine absorbs not only nutrients, but everything you eat. Toxic plant compounds, mycotoxins from spoiled food, bacterial metabolites, alcohol, that blood goes directly to the liver first. Over hundreds of millions of years of evolution, a liver capable of regenerating after toxic injury had enormous survival advantage. It is no coincidence that the Greek myth of Prometheus, the Titan, whose liver is eaten daily by an eagle and regrows nightly, comes from a civilization that observed animals and possibly performed ritual sacrifices examining organs. The ancient Greeks somehow knew. Not molecularly, but they knew. The liver regenerates, and this ability has changed and continues to change medicine far beyond what most people realize. Hexagonal, lobular structure reforms. Bile ducts reconnect. Architecture isn't identical molecularly, but functionally equivalent. Week 3. Imaging shows 75 to 80% of original volume restored. Rarely 100%. The liver rebuilds what's needed, not necessarily what existed. Younger people regenerate faster. Older, slower. Fatty or cirrhotic livers regenerate poorly. And here's the twist most people don't consider. There's surgery that uses this ability routinely. Living donor, liver transplantation. A patient with terminal liver failure needs a transplant, but no deceased donor is available. A healthy relative donates. Surgeons remove 60%, typically the right lobe, and transplant it. Now two people have partial livers. The donor retains 40%. The recipient receives 60%. Both regenerate. The donor's liver regrows within weeks. Mortality risk is about 0.2 to 0.5% in top centers. Not zero, but remarkably low for such major surgery. The recipient's transplanted fragment regenerates too, though in a more complex immunosuppressed environment. What's unsettling? More than half an organ removed, and the donor recovers. 2 weeks later, there's enough liver to leave hospital. 2 months later, volume nears normal. 6 months later, imaging barely shows loss. No other solid organ allows this. Hearts can't regenerate contractile tissue. Kidneys hypertrophy, but don't regenerate nephrons. Pancreas, new, lion, new, and regeneration doesn't require surgical injury. It also follows toxic damage. Severe acute viral hepatitis can destroy hepatocytes. If destruction isn't too rapid, the liver recovers. Chronic alcohol damage can partially reverse if drinking stops before cirrhosis, but cirrhosis replaces tissue with fibrotic scar that doesn't easily regress. What the liver cannot withstand is massive simultaneous destruction, overdose, acetaminophen toxicity, or fulminant hepatitis. Not lack of capacity, but speed of injury exceeding response speed. It's a race, and sometimes damage wins. Since the 1930s, a mouse experiment to 70% partial hepatectomy became the standard regeneration model. Remove 70% of a mouse liver. In 7 to 10 days, it regrows, reliable enough to underpin decades of research, thousands of papers, and still we don't know exactly how the stop signal works. Understanding that signal could transform therapy, stimulating regeneration in cirrhotic livers or controlling cancer growth, because hepatocellular carcinoma uses similar machinery to normal regeneration. Regeneration and oncogenesis are close relatives. Chronic regenerative cycles increase mutation risk. Inflammation favors mutated cell survival. Researchers aim to pharmacologically control these switches. In mice, regeneration can be induced in fibrotic livers with growth factors and antifibrotics. Translation to humans is slow and cautious, but the horizon is real. Pharmacological restoration of moderately damaged livers could redefine transplant need. Another frontier, liver bioengineering. Remove cells from a donor organ, leaving extracellular scaffold. Repopulate with recipient-derived cells. Rat models worked briefly. Scaling to humans is immensely complex. Billions of cells must populate correctly, and vasculature must function immediately. Not achieved yet, but biologically plausible. Meanwhile, medicine already uses regeneration surgically. Techniques like a LPPS force rapid growth of healthy liver segments before tumor removal. The liver grows to enable its own surgery. One overlooked aspect, regeneration is mainly driven by mature hepatocytes, not stem cells. Unlike intestine or bone marrow, differentiated liver cells partially dedifferentiate, divide, then redifferentiate, skilled workers temporarily reverting to apprentices to clone themselves. Rare in mammalian biology. Progenitor cells serve only as backup when hepatocytes are too damaged. Aging slows regeneration, proven in animal studies, but doesn't eliminate it. Adult human livers retain regenerative ability unmatched among solid organs. Evolution embedded redundancy to preserve it. Prometheus, chained and punished, had his liver eaten daily and regrown nightly. The Greeks lacked microscopes, but someone observed animals and noticed that reddish-brown organ behaving differently, returning when it shouldn't. They made it myth. Today, the same biology underpins life-saving surgery. Same organ, same regrowth. Context changes everything. And the final question isn't about the liver. It's about what else the human body can do that we haven't yet learned to use intelligently, what mechanisms lie dormant or active, awaiting discovery. We've partly learned the liver. The rest of the map still has blank regions.